Okay, part 3 of our foray into 4.3. Of course, this is divided into two parts. This is the first part, focusing primarily on f double prime and what it tells us about the graph of f. I've already gone ahead and done a lot of intro into this, so let's go ahead and jump right into an example. Okay, now remember that that is a product function, and so we should be able to surmise kind of what that looks like. Obviously, the domain is such that it's -3 to infinity, and I know that it's going to be, 1, 2, 3, that graph, times that graph, okay? And therefore, as a product function, I know that it's going to be 0, and then it's going to be negative, and then it's going to be positive. So I can surmise, based upon my knowledge of product functions and the two contributing functions, that it's probably going to look something like that. Okay? And if you don't remember how to do product functions or just any combination function, remember that when you're dealing with a combination function, this is a product function because it is a product of the outputs of x times the outputs of root x plus 3. But let's go ahead and get beyond the algebra 2 and the pre-cal, and let's actually get into the derivative. Now, let's do the first times the derivative of the second plus the derivative of the first times the second, okay? And that winds up being x over 2 root x plus 3 plus root x plus 3. Well, I know that I'm probably going to need to go ahead and get a common denominator, so let's go ahead and multiply that by, that denominator over itself. And we're left with x plus 2x plus 6 over 2x plus 3, or 3x plus 2 over 2x plus 3. That is my first derivative. Kind of a little bit hairy, but there you go. Now, once I'm here, I ought to be able to discern what I need in terms of critical values. Now, I need critical values, and critical values are where the first derivative is either undefined or 0. Well, let's go for 0 first. I know that there's going to be a critical value at x is equal to -2. Then I need to determine whether the denominator gives me any. Well, the denominator is undefined at x is equal to -3. Well, x is equal to -3 is the endpoint for the domain. So it's really not a maximum or a it's a maximum or a minimum, sure, because it's on the edge, but we really don't have to actually evaluate it or analyze it because it's right there on the edge of the implied domain. So we're just going to go ahead and go with the -2, okay? Let's go and plop it into a sign chart. Let's go -3, and let's start with the open interval, just so we don't get confused. And we go -2 to infinity, and we're going to go ahead and evaluate f prime. Now, I happen to know that at x is equal to -2, it's 0, okay? Now, anything that's greater than -3 is going to give you a positive radicand, and therefore a positive square root, and therefore a positive denominator. So basically, the only thing that's going to determine the positiveness or negativeness of this is going to be the numerator. And therefore, I know that anything that is between -3 and -2, when you plug it in for this x, is going to make this right here negative. So that's negative, and anything that's greater than -2 is going to make that positive. So we have that right there. Now, if I plug -2 into the original function in order to get its corresponding output, I'm going to get what? Well, I'm going to get -2, okay? So -2, -2, and I would actually write this out, and you're going to have to ask your teacher exactly how she wants you to write it, but you would say -2, -2 is the relative minimum, or in this case, it's actually the absolute minimum. The absolute minimum for this function, because it is the point at which the slope goes from negative to positive. Anytime you reveal a critical value at which the slope goes from negative to positive, you've revealed a minimum value. And then from there, we can go ahead and assign increasing and decreasing intervals. Increasing is obviously negative 2 to infinity. Decreasing is going to be negative 3 to negative 2. Now, here's what we're really in for in terms of 4.3. We're really interested in the second derivative. Let's go ahead and rewrite the original function. And then we'll rewrite f prime, and that's 3 x plus 2 over 2 root x plus 3. That's a nasty one. Well, let's go ahead and do it anyway. So we have f double prime of x. And actually, I mean, you can go ahead and pull this out as a coefficient, and that way we won't have to deal with it. We'll just take the derivative of the variable expressions, okay? And so we have the bottom times the derivative of the top minus the top times the derivative of the bottom. All of that over the bottom squared, right? And that's a little bit nasty, so let's go ahead and simplify it just a little bit. I know that in order to get rid of this is an implied denominator right here, right? So I need to multiply through by root x plus 3, root x plus 3. Well, that, when you distribute it to here, that winds up making this just x plus 3. And that winds up making this just 1/2 times x plus 2. Well, I guess what we could have done is we could have multiplied by 2 root x plus 3 in order to get rid of that and get rid of the fraction within the fraction. And what we wind up with is 2x plus 3. Well, that's going to be x plus 3 just in general, because the square root and the squaring cancel each other out. And so that's going to be to the 3/2. Well, that's 2x plus 6 minus x minus 2. So that's going to be 2x minus x, so that's x. And then plus 6 minus 2 is plus 4. And you can go ahead and take this 2 right here and sort of combine it with that one, and we'll kind of make that a 4 right there. And we get x plus 3 3/2. Now the factors in the denominator aren't really all that new, okay? They don't really give us anything, because what makes this undefined in the denominator is going to be negative 3, and there's nothing new about that. What's interesting is the only value that makes the numerator 0 is outside of the domain. So there are no second derivative critical values, okay? None. Which means that it's always concave up or always concave down. Well, for all the values that are going to be over here from negative 3 on, it's going to be positive over positive. So it's always going to be concave up. So it's concave up on negative 3 to infinity, okay? Now, that tells us a whole lot, okay? And actually, if we go ahead, and I got Grapher working on this one, it didn't crash on me this time, that is what the function looks like, which is actually pretty close to what we sketched out at the beginning. Notice that on the whole domain, it's going to be concave up, which is exactly what we talked about. And notice that it is concave down is decreasing between negative 3 and negative 2. That is indeed the minimum that we found, negative 2, negative 2, and then increasing from there. So our analytic work basically accords with what we found in terms of the graph that we've actually drawn. Now from here, I want to go ahead and do one more example, and of course we would feel left out if we didn't include a little bit of trig in here. So let's do a trig one. Nothing too nasty. Let's do, how about f of x is equal to x plus 2 cosine x. And let's go ahead and concentrate on just the interval 0 to 2 pi. That's going to help us because obviously this is a periodic function, and it's even with the x plus, it's going to wind up doing the same thing over and over and over again. It's just going to continue doing it, oscillating on the way up instead of just straight across. Because remember, 2 cosine x basically just oscillates over the y is equal to x the same way that 2 cosine x by itself would oscillate over the y is equal to 0. It's a sum function, right? So let's go ahead and do f prime is 1, and then of course the derivative of cosine is negative sine. So we wind up with that. Now, critical values are going to wind up being rather easy. That's going to be 0 is equal to 1 minus 2 sine x, or when sine x is equal to 1/2. Now, sine x is equal to 1/2, where? Well, that happens at pi over 6 and 5 pi over 6. Those are the only two places, because remember, I've limited myself to 0 to 2 pi. Okay? So those are my critical values. Let's go ahead and do a sign chart. And I know that it's going to be 0 to pi over 6. X is equal to pi over 6. Pi over 6 to 5 pi over 6. X is equal to 5 pi over 6. And then 5 pi over 6 to 2 pi. Zip. Right there. 0 and 0. Now, f prime, okay, let's go ahead and find a value for here. Now, since you know that it's actually going to extend back, this interval is actually going to extend back past 0, I can actually use 0 as a representative point if I wanted to. So let's go ahead and do that. Or you can just know that anything less than pi over 6 is going to give you a sine value that is less than 1/2. Okay, and therefore that makes this positive. Okay, in here I have pi over 2. Sine of pi over 2 is going to be 1. So that means 1 minus 2 is negative. And I know, let's use pi. Pi is a good representative point over here. At sine of pi, that's going to make this positive. So this goes up, down, and then up. Okay? That means that this, on this interval, is a maximum, and this, of course, is a minimum. I find the ordered pairs, and then I explain it. I explain the fact that this is a maximum because at that point f prime goes from positive to negative, and this is a minimum because at that point f prime goes from negative to positive. Okay? And of course the intervals increasing and decreasing are rather easy to do as well. Increasing, you know, from 0 to 2, remember this is on 0 to 2 pi, and yeah, let's go ahead and include the endpoints. Pi over 6, union, 5 pi over 6 to 2 pi, and you just have to ask your teacher whether she wants you to include the endpoints on that. Because when it's increasing, that's with respect to what's to the left and to the right of it. So officially there's nothing to the left of 0 because you've artificially limited the interval. I think you can go either way on that. And, you know, that's one of those ish things that never really bothered me. But just go ahead and ask your teacher about that. Now from here, we need to go ahead and do f double prime, because that's going to, and notice how this one, because it's trig and it's sine, winds up actually being a little bit easier than the radical one, because I know if f is equal to x plus 2 cosine x, and f prime of x is equal to 1 minus 2 sine x, then f double prime, well, that term is going to be 0, and that's just going to be negative 2 cosine x. Okay, well, negative 2 cosine x is equal to 0 is just, of course, where cosine x is equal to 0. And where's cosine x equal to 0? Yes, you're right. At pi over 2 and 3 pi over 2. Okay, if you do not have your unit circle values still in your memory bank, you need to go back and put them in your memory bank again. Okay? You're going to need them come time for the AP exam, and I am not there to give you cumulative quizzes, which I kind of wish I was. Okay, f double prime, I know that it's going to be 0 here and here. That's how I found those points, right? Now I know that if I plug in a representative point, let's say pi over 4, that's going to give me positive cosine value times a negative 2. It's going to be negative. Let's go and plug in pi. It's going to be a negative 1. Negative times a negative is a positive. And let's go ahead and plug in 5 pi over 4. Now it's actually 7 pi over 4 over here into there, and it's going to be negative once again. So concave, 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 like that. Okay? And your intervals, concave up, are going to be pi over 2, 3 pi over 2, and your interval concave down is going to be 0 pi over 2 union 3 pi over 2 to 2 pi. And of course you would designate this as a point of inflection, right, once you find the corresponding output, and that as a point of inflection once you find the corresponding output, and reason it out. Just basically say, well, you know, f prime changes sign from negative to positive here, showing that the concavity changes, and therefore that's a point of inflection, and the concavity changes, the second derivative changes from positive to negative, from concave up to concave down here, showing that that is another point of inflection. Well, again, let's go ahead and look at this function, and we know that if we go ahead and do x plus 2 cosine of x, let's go ahead and zoom out, and we go from, oh shoot, let's go ahead and, yeah, there we go. Let's go ahead and zoom in again. And I see that from 0 to 2 pi, which is going to be over here at about 6 1/4, right? I see the fact that it's going to be from 0 to pi over 6 is increasing, pi over 6 to 5 pi over 6 is decreasing, and then 5 pi over 6 on up to 2 pi is increasing again. I see the concavity is going to change right about here, which is at pi over 2, and it's kind of hard to see it on here on this longer upswing right here, but you can kind of see right about here that the concavity is going to change again from concave up, and then it's going to start in to be concave down for this hump right here. So it's somewhere right about in here for 3 pi over 2, okay? Now, that brings us kind of to the end of f double prime and how it communicates information about f and its graph. In the next maybe two videos, we'll go into the second derivative test. That's a little bit confusing, like I said, only because the name that it's given. But once you actually parse out that, it should be relatively smooth sailing, and it actually is necessary to know it for the AP exam. So please be on the lookout for that.